Hi everyone. Today I'll be explaining on kinetics of drug elimination. So I have drawn a blood vessel here. Now I'm giving a drug that is 100 microgram per ml. Once the drug is administered intravenously, it enters the blood and it is rapidly distributed to various tissues. It goes to different parts of the body. Now we are plotting a graph here by taking repeated blood samples. The fall in the plasma concentration of the drug as related to the time can be plotted, and from that we can find out the plasma T half. So we need to know what is this T half. T half is the time taken, that is the time duration in which the plasma concentration of the drug falls by 50% of the earlier value. So let's say we are given the drug at 0 minutes, okay, then later it has become 1 minute, and after that it has become 1 hour, and then 2 hours. So we are taking repeated blood sample, and the time taken for the plasma concentration to reduce to 50% of its value is known as T half. Okay, so here we have given 100 microgram per ml, and the time taken for the plasma concentration to reduce to 50 microgram per ml is known as T half. Regarding the first order kinetics, majority of the drugs will be obeying first order kinetics. In first order kinetics, a constant fraction of the drug is eliminated at a constant interval of time. So constant fraction, constant interval. For that, I have an example. The plasma concentration declining at a rate of 50% per 2 hours. So 100 microgram is the plasma concentration of the drug, and a constant fraction of the drug is eliminated in a constant time. So 1 by 2 is a fraction. 100 microgram per ml is getting reduced to 50 microgram per ml. That is getting reduced to 25 microgram per ml. That is getting reduced to 12.5 microgram per ml. That is getting reduced to 6.25 microgram per ml, and then to 3.575 microgram per ml, and then it is almost eliminated from the body. So if you look here, the fraction is constant, 1 by 2, 1 by 2, 1 by 2, 1 by 2, 1 by 2. So the time taken here, that is 2 hours, 2 hours, 2 hours, that remains same, and the fraction also remains same. So this is first order kinetics. Most of the drugs will be obeying this order of kinetics. Now, rate of drug elimination, that is the rate of drug elimination, is directly proportional to plasma concentration. So to prove that, I will explain with the same example which I have shown here. Suppose we increase the plasma concentration, like suppose we double it. So it is 200 microgram per ml is the plasma concentration. Now, even if we double it, then also the rate of drug elimination will be directly proportional to the plasma concentration. That means 200 microgram will take 1 by 2, that is 50%. The fraction will remain same, and the time will also remain same. So higher plasma concentration would also decline at a rate of 50% per 2 hours in this example. So that proves that rate of drug elimination is directly proportional to the plasma concentration. Then about the T half, so you can see that the time remains constant. So 100 is getting reduced to 50%, that 50, that is 50%. So the plasma concentration is like the plasma concentration, the T half is also remaining the same. So T half is constant in those drugs which are obeying the first order kinetics. Now, if the fall of plasma concentration is plotted against time, so here you have the plasma concentration on this axis and the time on this axis. Now, if we are plotting the plasma concentration against time, then the resultant plasma fallout curve would be curvilinear. This is a curvilinear graph. Now, the same graph, if you are plotting with logarithm on this axis, logarithm of plasma concentration on this axis and time on this axis, then the plasma fallout curve will be linear. And I also would like to show that the T half will remain constant in first order kinetics. Zero order kinetics. Hardly a few drugs will be obeying zero order kinetics in true sense. However, an example can be cited of ethyl alcohol or ethanol, whose metabolism is of zero order kinetics at virtually all the plasma concentrations. Now, there are certain characteristics features of zero order kinetics. They are a constant quantity of the drug is eliminated per unit time, or a fixed quantity of the drug is eliminated per unit time. For example, let us take the example of a drug which is having a plasma concentration of 50 microgram per ml. So plasma concentration is declining at a fixed quantity, let's say 25 microgram. So the drug is getting reduced to 25 microgram. Another 25 microgram is eliminated, so completely the drug is getting eliminated. So this is one example of the drugs that are following zero order kinetics. Now, this means that the rate of elimination is proceeding at a fixed rate independent of the plasma concentration of the drug. In other words, if you increase the dose of the drug, so initially it was 50 microgram per ml, now we are increasing to 100 microgram per ml. So we are increasing, and does not result in proportionate rise in extent of elimination. So even if we increase the dose, the drug is eliminated in a constant amount. So 100 microgram will get reduced to 75 and then to 50, 25, and then it is completely eliminated. So here we can see that higher plasma concentration will also decline at a rate of 25 microgram per hour in the case cited here. Hence, the T-half of these drugs which are following zero order kinetics are never constant. So what is T-half? T-half is the time taken for the plasma concentration to reduce to 50%. So 100 to 50. So it is taking 2 hours. And then to 50 to 25 it is taking 1 hour. So T-half is never constant in the drugs which are obeying zero order kinetics. Now, if we plot a graph with plasma concentration on this axis and time on this axis, then the resultant graph will be a linear graph. Now, if you are taking the logarithm of plasma concentration and time, then the plasma fallout curve will become curvilinear. Mixed order kinetics or Michaelis-Menten kinetics. Important drugs like phenytoin, digoxin, warfarin, decumeril, and aspirin in high doses will obey mixed order kinetics. It is a dose-dependent kinetics where smaller doses are handled by first-order kinetics, but as the plasma concentration reaches higher values due to increase in the dose, the rate of elimination becomes zero order because the metabolizing enzymes or the elimination process gets saturated at higher concentration. So that is the property of drugs which are obeying mixed-order kinetics. After a signal administration, if the plasma concentrations are plotted against time, the resultant plasma fallout curve will remain linear in the beginning and then it will become predominantly exponential. When the same are plotted on log scale, the plasma fallout curve will remain curvilinear in the beginning but become linear thereafter.